All right, questions? Where is everyone else? That is a good question. That's my question. Scared away from dynamic programming. Yeah.
For the project data sheet for the SRT, it looks a little bit different from last quarter's. I'm a bit confused for what you want us to do for the solution specifications.
Solution specification would be the details of how your solution is set up, right? So what's your project?
Making an app launcher.
A what?
App launcher.
Okay. So yeah, just details about the solution, basically.
Okay, so for the solution block program and the operation description, you just say what it does and give details.
Yeah, and those are basically suggestions, right? That's the kind of information we want. But if a block diagram makes sense, do that. If a set of pseudocode makes sense, do that, right? It doesn't have to be those very rigid titles for those blocks, right? It's sort of general information we want.
Thank you.
Mm-hmm. Do you have a question?
About PA4.
Mm-hmm.
Could you just explain a little bit about the BFS, the reversal? Like, how do you implement a queue, or how would you? What's the idea?
So the idea. So let's say this is our tree. All right, so we have the following algorithm. Insert the root, and then remove whatever's at the head of the queue, print its data, insert its children, and go back to the top, right? And quit if the queue is empty. So if this is our tree, what is this algorithm going to do? So here's our queue, here's the head, here's the tail. So we start off the whole process by taking the root of the tree, which is 20, putting that into the queue. So here's our 20. So let's number these steps 1, 2, and 3. So step 1, remove the head of the queue, pull out the 20. Print its data, so we print a 20, and then we insert the children of 20 into the queue. Well, it's got a left child, which is 10, and it's got a right child, which is 30. So we insert those into the queue. And we go back to step 1. Remove the head of the queue is 10, print its data as 10, inserts its children. Well, 10 has no children, there's nothing to insert. Go back to step 1. Remove the head of the queue, which is 30, print its data 30, insert its children. Well, it has a 25 and a 45. So insert those into the queue, and we just keep looping, right? Remove the head is 25, print its data, insert its children, it has no children. Remove the head of the queue 45, print its data, insert its children, which is 50. Remove the head of the queue is 50, print its data, insert its children, it has no children. Now we try to remove the head of the queue is empty, we're done. That's your breadth first search traversal. So you can use the same queue that you used in a previous assignment, but instead of just inserting integers, we want to actually store these tree nodes. Because when we remove something from the queue, we need not just its data value, but its children also, right? So print temp arrow data, and then insert temp arrow left if it's not null, and insert temp arrow right if it's not null. Make sense? Cool. Other questions? Other PA issues? So let's go back to this business of a longest common subsequence.
I watched your video from the second
Yeah?
Or at least I started watching it.
Mm-hmm.
It's come out real nice.
Okay, good. Good. All right, so longest common subsequence. So let's look at some sequences. So remember, the goal here is to find within each of these some ordered collection of letters that's common. Right? For example, we have an A followed by a B, and down here we have an A followed by a B. We also have a G followed by an A followed by a B, and here we have a G followed by an A followed by a B. And that's probably our longest common subsequence. Do we have a T? Oh yeah, we have a G and a T and an A and a B, right? And we can think of this as if we draw lines to make these associations, right? These lines can't cross. That's what we mean by preserving the order. But if we can find a sequence of associations like this, right, those letters correspond to a common subsequence. Now we're looking for the longest possible common subsequence. And we broke this down to two cases. This was where we left off yesterday. So consider the following possibilities. Right, these don't have to have the same length. They could be totally different length sequences. But suppose this ends with some particular letter. I'm just going to use X, but it does not have to be the letter X. It's a variable, right? Suppose that both of these strings end with the same letter. Okay, if we find the longest common subsequence between this original string and this original string, do you agree that that common subsequence is going to end with the letter X? Right? Intuitively, if we were to draw this line here, that's not going to cross any of the other lines that we have in here. So there's no reason not to include X in a common subsequence. Additionally, in our longest common subsequence, everything other than that last X is going to be a common subsequence to these two strings. Does that make sense? So if you find the longest common subsequence to your two original strings, it's going to end with this last letter, and everything up to that is going to be something in common between this subsequence and this subsequence. Okay, so that lets us have our first case. So longest common subsequence of string M with length M and string N with length N. And so it's going to be 1 plus the longest common subsequence of these substrings. If the last letter of each string is the same. Okay, our second case is where this last character is not the same. So if the last letter is not the same, then there's exactly two possibilities. Possibility 1, the longest common subsequence between your two original strings might end with this character, whatever x is. Right, so the longest common substring might end with x, or the longest common substring does not end with x. Right, that's kind of obvious. Whatever the longest common substring is between your two strings, it either ends with x or it does not end with x. Okay? If it ends with x, then we have a substring to this original string, and it's also got to be a substring to this shortened second string. Because if that common subsequence ends with an x, it can't include this last character y, because that's different from x. So in case 1, the LCS is part of the first m characters of string m and the first n minus 1 characters of string n. So I'm saying this is m and this is n. Right? So if our common subsequence ends with this letter x, it's got to be a subsequence of this smaller version of n. Which means the LCS is a common subsequence to these two strings. So the LCS of our two original strings equals the LCS of these two strings. The other possibility is the least common string does not end with an x, and now we have the exact opposite situation. It's still going to be a substring of n, but it's going to have to be a substring of this shortened version of m. Because if it doesn't end with x, right, it's not going to include the x. So it's got to be a substring of this shortened sequence. So if the LCS does not end with x, then the longest common substring of our original strings is also the longest common substring where we shorten that first string by 1 character. So those are our 3 cases. If the last character is the same, then our longest common substring is 1 plus the longest common substring when we shorten both strings by 1 character. Otherwise, the longest common substring is either this or this. We don't know which, but if we simply find the greatest value of these two, that'll be the length of our longest common substring. So it's simply the max of these two expressions. And there's a recursive formula for the longest common substring.
You're just like crossing out numbers,
Kind of, yeah. Okay. But the recursion looks pretty weird when you do this.
And what happens when the strings are of different lengths? Don't you run risk of potentially segmenting?
Well, it's perfectly fine if they're different lengths, but we need an edge case here.
Yeah, one of them's null.
Right, so if m equals 0 or n equals 0, return 0. There's your base case.
What happens when x and y are both not in the larger string?
That's okay, because we didn't require that it's in either of them. Up here, we simply had 2 cases where their LCS ends with x or does not end with x. Right? So if it doesn't end with x, it could end with y, but it might not. That's fine. Right? Because if the largest common subsequence does not end with an X or a Y, right? It's certainly an LCS of this string and this string, right? Which means it's also the LCS of this string and this string,
Okay.
because those extra characters aren't going to change
It's because
common subsequence.
yeah, I get it now. Because if X is a part of the substring, whatever it is,
Yeah.
then you know Y can't be because X was on the end. And
Right.
if X isn't, then you could just take X out.
Yes, exactly. So this is kind of edgy, right? This is the way that these things generally feel. It's okay if it seems kind of confusing, right? But you want to try to work through this and see that this works. And you'll encounter this again, right? You'll see this in future courses. So it's not like this is your only chance to grasp it. But this is, for most of us, an initial introduction to this. And it's similar to how all these things are going to look and feel with dynamic programming. So I was bored last night, so I wrote some code. So let's look at some code. So here's some code for finding the longest common substring of two strings. So LCS will take two strings, and we'll also take two integers saying how many characters are in those strings, and it'll return the length of the longest common substring. All right, so my main program, so I cut everything off at 100 characters just to avoid going crazy with mallocs. So I got two input strings, S1 and S2. I input these with fgets. I get rid of the new line at the end because I don't want to deal with non-printable characters. And I call LCS. I pass S1 and S2 along with the number of characters, and I print out what the longest common substring is. So let's play with this first. So let's do hello and ELO. And the longest common substring has a length of 3. And I'm also showing you each time that I call LCS what I'm passing to it. So initially I'm working on hello and ELO. And the last character is the same, the O and the O. So now it's going to try to find the longest common substring between hel and L. And then it's going to add 1 to that length. Well, those have the same last character, so now it's recursing again and working on HEL and E. And it's going to find the longest common substring, add 1 to that, and then eventually add 1 to that. And HEL and E have different last characters. So it's going to work on HE and E. And there should have been another, but then when it works on HEL and the prefix to E, right, that has a length 0, so it doesn't find anything. So it's working on HE and E, and that's going to be 1 plus the longest common substring between H and an empty string. So that'll give you 0, and it'll add 1 and pop back up, and eventually you'll get to 3. So here's a longer test. So here's two strings that I kind of typed at random. And let's see what this does. So lots of recursion.
I take it on K5, you don't want us to show this.
Yeah, but pause like 5 seconds between each line so I can read it, right?
Looks like it's doing G by itself a lot.
It is, yeah. There we go. Longest common substring has length of 13. And we could probably figure out what it is from there. So how many times did it recurse? 89,774, give or take. Right? And these are short strings. So this is a frightening amount of recursion. It was printing mainly, so if we just put it in detail, it comes back pretty quickly. So here's test 3. So these are a little longer. And I don't know if this will finish or not. It finished somewhere during Netflix last night. But it takes a lot, and I think it was yeah, so it was 2 billion iterations, right? And these strings are not like all that long. So this is fairly expensive. So let's see how this works. We did the main program. Here's LCS. So base case, if the length of A or the length of B are less than or equal to 0, I just return a 0. Right? There's no common substring if there's no letters in one or both of the strings. I made my own print routine because these strings are not necessarily null terminated because we're mucking with the length. So print just prints out the first len A characters of A. So that's just the echo printing out. So here's the only real work is right here. So if the last character of A is the same as the last character of B, call LCS on the shortened strings, add 1, return that. Otherwise, call LCS with the second string shortened, call LCS with the first string shortened, and return whatever the largest value was. That's it. Right? It's really, really short, but yet it runs, 2 billion times with a string about 25 characters long.
That's the price you pay for recursion.
Yeah. It can be really kind of horrifying, but in a slightly glorious way. So
There is a better way of that.
nope, that's the only way.
Well, I'm sure you could, you might be able to skip a step or two to make a case where they're both not part of the recursion. But that would be
Possibly, yeah.
checking, so that would not actually fix much.
Mm-hmm.
You make it linear.
Actually, that would makes it good in the brute force, because then you could test it with everything else to see if this even in the other string, but
Right, right.
that would still take up resources.
I'm going to bite the bullet and go on the wireless here, and because I want to show you something. Assuming I can get a connection. There we go. Today. Sorry. So there's this thing called Ackermans Function. It's a classic recursive function, and it's pretty fun to code up. But it feels similar to what we're seeing here with longest common subsequence, because the definition of it is misleadingly simple. Should have PDF'd this earlier. Anyway, it's a recursive function. It has 2 arguments to it, and its definition is a simple combination of earlier versions, right? Versions of the function on smaller things. So here's Ackermans function. So Ackermans of m comma n. If m is 0, it's just n plus 1. That's easy. If n is 0 and m is positive, it's a of m minus 1 and 1. And in the general case, it's a of m minus 1 comma a of m n minus 1. Right, so we're always counting down, so we're not going to recurse indefinitely. And when we get down to m equals 0, we'll have our base case. But the computational complexity of this is shocking. It's large enough that you need a new form of writing numbers to be able to describe it. So we have this up arrow notation from Donald Knuth that we can use to describe the complexity of this. So Ackermans of 1, 2 turns out to be 4. That's pretty easy. Ackermans of 4, 3, you got to do all of this, and it ends up being 2 to the 2 to the 65, 536 minus 3, right? That's just 4 comma 3. And the numbers that you get to, like for 5 comma 1, right, we need this up arrow notation, which is like 2 raised to the 2 raised to the 2 kind of thing.
What's the application of this function?
It's fun.
It's a good demonstration. So
I can see that you can make those numbers, but what's the point?
So
the dynamic program, where did it come from?
can be used as a benchmark of a compiler's ability to optimize recursion. There you go.
That's true.
It's an interesting object in theories of computation and complexity analysis, where we're studying, the growth rate of complexity of different algorithms and things like that. It's a really interesting kind of outlier data point, but not really an outlier in the sense that it's alone, but it's deliberately a simple definition that just takes ridiculous amounts of iterations to calculate. Yeah.
So recursive, right? That it's defined as like it's a type of not recursion. Dynamic is a type of recursion, but instead of like splitting it up, kind of trimming it down.
Yeah, dynamic programming in general is this idea of breaking a problem into subproblems, right? Into smaller versions of the problem. Kind of like we do with divide and conquer, but not necessarily just cutting in half.
Okay, so cutting things in half is part of dynamic programming.
Yeah, that's a version of dynamic programming. But dynamic programming is more general. It's when we can express a particular problem in terms of the solution of subproblems, smaller problems, and then put together those solutions to get to our better solution. So let's look at what happens if we want to know what the largest common subsequence is, right? And so you need to do something besides just recording, the length of the LCS plus 1, or the maximum length of the LCS of the substrings. You need to also record what the substring is itself. And the only difference here is just some kind of annoying housekeeping you have to do. And it actually took a couple of tries to find the right algorithm, which was I decided that I would only null terminate the return from LCS. Everything else, no null terminators. And so LCS returns, instead of an integer, it actually returns a pointer to a string, which is the longest common subsequence. So all of this stuff looks the same. LCS changes, but it's not a huge change. So if either length is 0, then I just return a string of length 0. But I got to do that malloc there. That's the only malloc in the whole program. But it's on top of these 0-length strings that you're going to build all your other strings. For some reason, that seems weird. So I allocate 100 bytes. I set a null terminator in the beginning, and I return that if there's no common subsequence. Otherwise, I echo out the subsequences that we're working on. And then if the last character is the same, I have a, this is just some null terminator gymnastics. Call LCS on the substrings, right? That's going to return a pointer to a string, which is the longest common subsequence. I store that in a temporary variable return. And I want to stick one more character onto it, right at the end, where the null terminator is now. So this middle line, I basically add an extra null terminator after the current null terminator, because I'm going to overwrite the current null terminator with a new character. And once I do that, I can't use things like string length. So I use string length plus 1 to stick an extra null terminator on, and then I replace the original null terminator with the last character of A or B. They're the same. So that's appending one character to the end of my string, and I return that, but it's keeping it null terminated. Otherwise, call LCS on the two substrings, right? Save each of those as a pointer, and then whichever one is bigger, just return that one as our longest common subsequence. So almost identical to the first version, right? You just got to sort of get things lined up the right way. So this will actually give you the common substring. So there were my original strings, and the longest common substring was SAJ. And for test 2, let's put that in detail. So there's the longest common substring for test 2. And for test 3, it's doing more work. Oh yeah, you're right. All right, so we won't do that. That's what test 3 was. All right, so yeah, so how do we do better, right? How do we make this thing tractable? Right, so test 3 took 2 billion recursive calls to finish. So, well, we're going to cache the results from calling LCS. So I have a two-dimensional save array, okay, 100 by 100. The main program's exactly the same. LCS is almost exactly the same, except in the very beginning, I check this save array. And the beginnings of my strings never change, right? I'm working on this string and that string. And I may be working on smaller versions of it, but all I'm doing is taking the first 5 letters or the first 7 letters or the first 10 letters. I'm not actually changing any of the letters. So all I need to know is sort of how many letters am I taking from the first string and how many from the second string, right? And I don't have to actually store the strings themselves. So I have a two-dimensional array up here, and I index it with the length of the first string, the length of the second string. And if that entry is null, I have not yet calculated the longest common subsequence for those two strings. But if I calculate it, then that entry will not be null, and I'll just return whatever the longest common subsequence was. So this is a two-dimensional array of strings. So I just check to see if I've calculated, and if I have, I'll return. Otherwise, we do the same thing we did before, right? See if the last character is the same and do this. If not, do the thing that we did with different ones. But at the end, I save my result. So I make that entry in my save array point to 100 bytes, and I copy my longest common subsequence into it. And I do that in both cases that give me an answer. And now the next time that I try to calculate my longest common subsequence where the first string has len A characters and the second has len B, I'll have an entry stored in my save array, and I'll just return that without doing any further recursion. So there's the result on test 3. And instead of 2 billion calls, it took 497. Okay, and this is something we find a lot in dynamic programming when we have repeated subcases, right? So someone noted that it seemed to be checking J a lot, comparing it to other things. If you go through that whole list of 2 billion calls that were made in this case, most of them are going to be the same, right? Our strings have maybe 25 characters in the beginning. There aren't 2 billion ways that we can pull possible substrings out of that, right? We can use the product rule. We've got 25 options for the first string, 25 for the second. That's about 600 possibilities. And so the first time that we calculate one of the subsequences, we can just use that result every subsequent time that we want to do the same calculation. So this really prunes the heck out of the search tree, and it makes it, you know, doable more or less instantaneously. Did we do this with Fibonacci numbers yesterday? We didn't. Okay.
So we could do it iteratively, or we could do it recursively.
The ODP is readable again, by the way. I had a permission error, which most people noticed. So I posted an announcement. All right, so let's generate Fibonacci numbers, right? So we'll just print out the ith Fibonacci number. So base case, if our number is less than or equal to 1, we'll return a 1. Otherwise, we'll find fib of I minus 1 plus fib of I minus 2. We'll add those together, and we'll return that. We're going to do everything a few times. So there's our first few Fibonacci numbers, and you can see it's slowing down pretty drastically. Right, and fib 45 will take a long time. And then your answer is bigger than 32 bits. But if we let it keep going, it would just go negative. So what's going on here? It's calling fib over and over again.
So when it calls fib minus 1, it also has to calculate fib minus 2.
Mm-hmm. So let's see how many times it's calling. So we'll make a global count variable. And each time that we come into fib, we'll increment count. It's global. Evil global. So, so we'll initialize it before our call in main, and inside fib, each time that we call fib, we'll bump up count, and then we'll print out the value of count once we've come back from our initial call. And you can see what's happening is the number of calls is growing roughly on par with the Fibonacci number itself. And so by the time we get up to 45, we're going to be recursing a few billion times, and that's just taking lots of CPU time. Can we do longs? I knew I'd get in trouble somewhere. All right. All right, so no chance of finishing here, right? So let's save our results. So we'll make an array of 1,000 integers to save our Fibonacci values. We'll initialize it to 0. I guess I'm going to make this global too. So we'll cache our results. So in our Fibonacci code, we're going to do the following. So if save bracket I is not equal to 0, we're just going to return that saved value. So initially, all the entries in our save array will be 0. So the first time we come through, save I will be 0. We won't do the return. So we got to actually do some work. So we've got to actually calculate the nth Fibonacci number using our recursion. But at the very end, before we return, we're going to save that result in our array. So we'll just save it at entry I. And there's your first 1,000 Fibonacci numbers. And in most cases, our number of calls to the fib function was 3. Right? Why? Because by the time we're calculating fib 24, we've already calculated fib 23 and 22, which means we've saved them in our cache, which means when we try to calculate fib 24, we have to call fib 23, 22, but they don't recurse. They just read from the array and come right back. So this is extremely efficient. My longs didn't actually go long, though. They still blew up after 45. Yeah, because long is probably the default, right?
I mean, having it unsigned is probably.
That's true.
I guess I can log that and
Yeah, it's gonna blow up.
Nope, that still blows up. Yeah, I've never. That's weird.
It goes a bit farther.
So is the int isn't applied if you say long and long long?
I think so.
Just do long long int. Try that.
No, but I didn't make my save array. Nope. I'll figure that out later. Anyway, so that's the idea, right? Recurring subcases and caching them up. And it often makes a huge difference in your performance. I just like teasing them. Usually, if you have a need for a global variable, there's nothing wrong with using a global variable, right? And this is a perfect case where you don't want to be passing the save array to a function because you want one save array, right? You don't want it to be local to a context. Same thing with the count of how many times we call this. We don't want to pass that as an argument because we want one copy that everybody touches and updates, right? But it's easy to get kind of reckless with globals and say, I don't like passing arguments to functions, so I'm just going to make 1,000 different global variables, and these will be the variables this function uses, and these will be the variables that function uses, and then you've got something that's potentially a mess to work with and maintain. That's all.
Aren't global variables more useful when you're doing object-oriented stuff because objects can reference other objects variables?
Well, when we get to objects, we have a great deal of control over the scoping of variables and code. And yeah, in some cases that'll make good sense.
I know in Unity, whenever I was doing games and that, most of the variables ended up being global.
Yeah.
Most basic variables ended up being
Right. Yeah, that makes sense. Yeah, so if you're doing large simulation, right, you might have a time base that's ticking based on certain events, and I would probably make that global because every piece of code is going to want to access that, and we really don't want different versions of it, right? It really intuitively belongs in sort of a global scope. So yeah, there's good reasons to use it.
I mean, both those object-oriented languages, those
those aren't really globals because they belong to the object itself.
Do they? Okay.
That is true, like, but there's, I guess it's the difference between like it's a putting a public float would probably be putting that.
Well, public's just exposing
Yeah, it would
the visibility of it.
I think what you're thinking about is static. 'Cause
Yeah, I don't know the specifics of what you're thinking of in Unity.
Yeah, that was a C#.
Okay.
Which is should still have a lot of the same ideas behind it, but like mainly how the public and the private was through the editor itself.
Mm-hmm.
If it was public, then it would show up in the editor. If it was private, it would not.
Yeah.
You could still access private things, but if it was, I know if it was a global variable, it was accessible. Much easier.
So if I'm doing a simulation in straight C, right, and I've got this timestamp that's rolling, right, I would make that global.
That should be global. Yeah.
But if you're in an object-oriented language or environment, you don't really need to do that, right? And the clean way to do it would be to have an object that represents your time or that stores your time. And when you want to read it, you access a method from that object, right? Maybe a static method. And when you want to update it, you hit a method. And so it's not really global, but it's globally accessible, right, without having to pass it. So you can do things like that.
Yeah, there's a specific object inside of it that has the script attached.
Yeah. And let's be honest, when you get down to machine code, everything's global, right? Just like everything is a jump, right? Most of your loops and things like that code up in assembly language as jumps. Not always. There are some languages that do branching, looping at the assembly level. All right, so tomorrow we want to talk about rod cutting, and we want to talk about the knapsack problem, and your fifth PA is going to be on the knapsack problem instead of longest common subsequence. So we'll talk about those problems in some detail. We'll talk about the overview of PA5, and then we'll go from there. And rod cutting will be an example of dynamic programming with a different feeling from the cases we've been looking at. And this will also get us to talking about greedy algorithms, which is another class of algorithms. All right, so I will see you tomorrow.
How would you do this, or if when